In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about silicon solar cell one-dimensional. This tutorial uses a simple one-dimensional model of a silicon solar cell to illustrate the basic steps to set up and perform a device physics simulation with the semiconductor module. A user-defined expression is used for the photogeneration rate, and the result shows typical current voltage and power voltage curves of solar cells. The carrier generation mechanism from the photovoltaic effect is not modeled in detail. Instead, a user-defined expression is used for the total generation rate based on Beer's law, with the empirical silicon absorption spectra and an approximated for AM 1.5 spectra. The Shockley-Read-Hall model is employed to capture the main recombination effect. Under normal operation conditions, photogenerated carriers are swept to each side of the depletion region of the p-n junction, and a small forward bias voltage is applied to extract the electrical power given by the product of the photocurrent and applied voltage. Analyzing a silicon solar cell design with the semiconductor module. When analyzing semiconductor devices, it's important to account for the multiple physics affecting their performance. The semiconductor module and add-on product to COMSOL multiphysics software can help you model these complex devices. In this simulation, we discuss a new tutorial model of a one-dimensional silicon solar cell, which is available with the latest release of COMSOL software version. The far-reaching application of solar cells. Solar or photovoltaic cells are used for applications such as recharging batteries in homes and even powering spacecraft. For instance, NASA Juno spacecraft completed a mission to Jupiter partly thanks to the performance of its solar cells. The power generated by solar cell enabled Juno to gather new information about Jupiter, helping scientists to learn more about the planet. And the chapter of NASA's Juno spacecraft breaks solar power distance record. NASA's Juno mission to Jupiter has broken the record to become humanity's most distant solar-powered emissary. NASA's Juno mission to Jupiter has broken the record to become humanity's most distant solar-powered emissary. The milestone happened at 11 a.m. on Wednesday, January 13, when Juno was about 493 million miles, which is about 793 million kilometers from the Sun. The previous record holder was the European Space Agency Rosetta spacecraft, whose orbit peaked out at the 492 million miles or 792 million kilometers mark in October 2012 during its approach to comet 667P Kurumov-Gerasimenov. Juno is all about pushing the edge of technology to help us learn about our origins, said Scott Bolton, Juno principal investigator at the Southwest Research Institute in San Antonio. We use every known technique to see through Jupiter's clouds and reveal the secrets Jupiter holds of our solar system's early history. It just seems right that the Sun is helping us learn about the origin of Jupiter and the other planets that orbit it. Launched in 2011, Juno is the first solar-powered spacecraft designed to operate at such a great distance from the Sun. That's why the surface area of solar panels required to generate adequate power is quite large. The 14 Juno spacecraft carries three 30-foot long or 9-meter solar arrays fastened with 18,698 individual solar cells at Earth's distance from the Sun. The cells have the potential to generate approximately 14 kilowatts of electricity, but transport those same rectangles of silicon and gallium arsenide to a fifth rock from the Sun distance, and it's a powerfully different story. Jupiter is 5 times farther from the Sun than Earth, and the sunlight that reaches that far out packs 25 times less punch, said Rick Nabanken, Juno's project manager from NASA's Jet Propulsion Laboratory in Pasadena in California. While our massive solar arrays will be generating only 500 watts when we are at Jupiter, Juno is very efficiently designed and it will be more than enough to get the job done. Prior to Juno, 8 spacecraft have navigated the cold, harsh underlit realities of depth space as far out as Jupiter. All have used nuclear power sources to get their job done. Solar power is possible on Juno due to improved solar cell performance, energy efficient instruments, and spacecraft. A mission design that can avoid Jupiter's shadow and a polar orbit that minimizes the total radiation. Juno's maximum distance from the Sun during its 16 months science mission will be about 570 million miles or 832 million kilometers, an almost 5% increase in the record for solar-powered space vehicles. It is cool we got the record and that our dedicated team of engineers and scientists can chalk up another first in space exploration. But the best is yet to come. We are achieving these records and venturing so far out for a reason, to better understand the biggest world in our solar system and thereby better understand where we came from. Juno will arrive at Jupiter on July 4th of this year. Over the next year, the spacecraft will orbit the Jovian world 33 times, skimming to between 3,100 miles or 5,000 kilometers above the planet's could tops every 14 days. During the flybys, Juno will probe beneath the obscuring cloud cover of Jupiter and study Jupiter's aerorate to learn more about the planet's origin, structure, and atmosphere, and also magnetosphere. NASA's Jet Propulsion Laboratory, Pasadena, California, manages the Juno mission for the principal investigator and Scott Burton of Southwest Research Institute in San Antonio. Juno is part of NASA's New Frontier program, which is managed at NASA's Marshall Space Flight Center in Huntsville, Alabama. Lockheed Martin Space Systems Denver builds the spacecraft. The California Institute of Technology in Pasadena manages GPL for NASA. For applications like the Juno mission, to be possible, the solar cells involved need to be designed and analyzed accurately. In particular, engineers must pay special attention to the semiconductor materials. The semiconductor materials in solar cell absorb light, which is eventually converted into electricity. Thus, understanding how semiconductor materials such as silicon function within these solar cells is essential to accurately analyzing their performance. And what about the solar photovoltaic cell basics? When light shines on a photovoltaic or PV cell, also called a solar cell, that light may be reflected, absorbed, or pass right through the cell. The photovoltaic cell is composed of semiconductor materials. The semi means that it can conduct electricity better than an insulator, but not as well as a good conductor like a metal. There are several different semiconductor materials used in PV cells. When the semiconductor is exposed to light, it absorbs the light's energy and transfers it to negatively charged particles in the material called electrons. This extra energy allows the electrons to flow through the material as an electrical current. This current is extracted through conductive metal contacts, the grid-like lines on solar cells, and can then be used to power your home and the rest of the electric grid. The efficiency of photovoltaic cell is simply the amount of electrical power coming out of the cell compared to the energy from the light shining on it, which indicates how effective the cell is at converting energy from one form to the other. The amount of electricity produced from photovoltaic cells depends on the characteristics such as intensity and wavelength of the light available and multiple performance attributes of the cell. An important property of photovoltaic semiconductor is the band gap, which indicates what wavelength of light the material can absorb and converts the electrical energy. If the semiconductor's band gap matches the wavelength of light shining on the photovoltaic cell, then that cell can efficiently make use of all the available energy. Learn more below about the most commonly used semiconductor materials for photovoltaic cells. And what about the silicon as a material? Silicon is by far the most common semiconductor material used in solar cells, representing approximately 95% of the modules sold today. It is also the second most abundant material on Earth after oxygen and the most common semiconductor used in computer chips. Crystalline silicon Crystalline silicon cells are made of silicon atoms connected to one another to form a crystal lattice. This lattice provides an organized structure that makes conversion of light into electricity more efficient. Solar cells made out of silicon currently provide a combination of high efficiency, low cost, and long lifetime. Modules are expected to last for 25 years or more, still producing more than 80% of their original power after this time. And what about the thin film photovoltaics? A thin film solar cell is made by depositing one or more thin layers of photovoltaic materials on a supporting material such as glass, plastic, or metal. There are two main types of thin film photovoltaic semiconductors on the market today: cadmium telluride or CdTe and copper indium gallium diselenide. Both materials can be deposited directly onto either the front or back of the module surface. CdTe is the second most common photovoltaic material after silicon, and CdTe cells can be made using low-cost manufacturing processes. While this makes them a cost-effective alternative, their efficiencies still aren't quite as high as silicon. CIGS cells have optimal properties for photovoltaic material and high efficiencies in the lab, but the complexity involved in combining four elements makes the transition from lab to manufacturing more challenging. Both CDTE and CIGS require more protection than silicon to enable long-lasting operation outdoors. And what about the perovskite photovoltaic? Perovskite solar cells are a type of thin film cell and are named after their characteristic crystal structure. Perovskite cells are built with layers of material that are printed, coated, or vacuum deposited onto an underlying support layer known as substrate. They are typically easy to assemble and can reach efficiencies similar to crystalline silicon in the lab. Perovskite solar cell efficiencies have improved faster than any other photovoltaic material, from 3% in 2009 to over 25% in 2020. To be commercially viable, perovskite photovoltaic cells have to become stable enough to survive 20 years outdoors, so researchers are working on making them more durable and developing large-scale, low-cost manufacturing techniques. And what about the organic photovoltaic? Organic photovoltaic, or OPV cells, are composed of carbon-rich organic compounds and can be tailored to enhance a specific function of the photovoltaic cells, such as band gap, transparency, or color. OPV cells are currently only about half as efficient as crystalline silicon cells and have shorter operating lifetimes, but could be less expensive to manufacture in high volumes. They can also be applied to a variety of supporting materials, such as flexible plastic, making OPV able to serve a wide variety of uses. And what about the quantum dots? Quantum dots, solar cells conduct electricity through tiny particles of different semiconductor materials, just a few nanometers wide, called quantum dots. Quantum dots provide a new way to process semiconductor materials, but it is difficult to create an electrical connection between them, so they are currently not very efficient. However, they are easy to make into solar cells. They can be deposited onto a substrate using a spin coat method, a spray, or roll to roll printers like the ones used to print newspapers. Quantum dots come in various sizes and their bandgap is customizable, enabling them to collect light that's difficult to capture and to be paired with other semiconductors. Like these kind, to optimize the performance of a multi-junction solar cell. More on those below. And what about the multi-junction photovoltaics? Another strategy to improve photovoltaic cell efficiency is layering multiple semiconductors to make multi-junction solar cells. These cells are essentially stacked or different semiconductor materials as opposed to a single junction cells, which have only one semiconductor. Each layer has a different band gap, so they can absorb a different part of the solar spectrum, making greater use of sunlight than single-junction cells. Multi Multi-junction solar cells can reach record efficiency levels because the light that doesn't get absorbed by the first semiconductor layer is captured by a layer beneath it. While all solar cells with more than one band gap are multi-junction solar cells, a solar cell with exactly two band gap is called a tandem solar cell. Multi-junction solar cells that combine semiconductors from column 3 and 5 in the periodic table are called multi-junction 3 and 5 solar cells. Multi-junction solar cells have demonstrated efficiency higher than 45%, but they are costly and difficult to manufacture, so they are reserved for space exploration. The military is using 3 to 5 solar cells in drones, and researchers are exploring other uses for them where high efficiency is key. What about the concentration photovoltaics? concentration for concentration photovoltaic, also known as CPV, focuses sunlight onto a solar cell by using a mirror or lens. By focusing sunlight onto a small area, less PV material is required. photovoltaic materials become more efficient as the light becomes more concentrated. So the highest overall efficiencies are obtained with CPV cells and modules. However, more expensive materials, manufacturing techniques, and ability to track the movement of the sun are required. So demonstrating the necessary cost advantage over today's high-volume silicon modules have become challenging. The semiconductor module serves as a valid tool for analyzing these designs and accounting for all relevant physical effects. To better understand the functionality included in this add-on product, let's explore the silicon solar cell one-dimensional tutorial and new with the release of capsule multiphysics version, last version. Modeling a silicon solar cells with a semiconductor module. The solar cell model is comprised of a one-dimensional silicon p-n junction that includes a Shockley-Read-Hall recombination and carriers generation. Typically, the photon generated carriers in a silicon solar cell are swept to each side of a p-n junction's depletion region. We can then they extract electrical power by applying the small forward bias to the solar cell. The power is given by the product of the applied voltage and photocurrent. The goal of the model is to predict a silicon solar cell's behavior under this forward bias and with an applied voltage between 0 and 0.6 volt. Let's take a look at the silicon p-n junction, which we formed by a p-doping and the front surface of n-type silicon wafer. This n-type silicon wafer is created by uniform bulk n-doping, both from of doping from front surface and uniform bulks are easily accounted for by using a geometric doping model feature and an analytic doping model feature, respectively. We use a boundary selection for doping profile node to define the surface and add two metal contact features to specify the electrical connection between the front and back surfaces. We account for the main recombination effect with the Shockley-Read-Hall recombination model implemented via trap assisted recombination feature, and to simplify this model we add an arbitrary user-defined expression to represent the generation rate with the user-defined generation feature. By doing so, we can avoid detailed modeling of the photovoltaic effects carrier generation mechanism. It is also possible to add sophisticated expressions to make this model more advanced. For example, we can combine it with ray optic simulations to compute the silicon solar cell's performance for a certain date and location, as described in the silicon solar cell with array optics demo applications. Next, let's discuss the results from the model. The chapter of evaluating the performance of silicon solar cells in capsule multiphysics. The first plot compares donor and acceptor concentrations for up to 10 micrometer beneath the solar cells from uh, front surface, as we see below. While the donor concentrations remain the same, acceptors concentrations sharply decrease. To avoid accidental setup errors, it is a good practice to check a model's doping profile. We can also investigate the Shockley-Read-Hall recombination rate and user-defined photogeneration rate for the entire cell's thickness. The Semilog plot below shows that, as expected, the user-defined expression for a single exponential function is a straight line. Finally, we plot the solar cell's current voltage and power voltage curves. This enables us to visualize a few of the cell's essential operating parameters, including the max power, which is about 6.8 microwatt, short circuit current, which is about 14 milliampere, and open circuit voltage, which is about 0.57 volt. Both the current voltage and power voltage curves generated by this model match those of typical solar cells, helping to verify the accuracy of the semiconductor module. The tutorial model we discuss here is only one example of how we can use the semiconductor module to write it yourself with a step-by-step instruction for setting up and running the simulation by clicking the this and downloading this simulation. Designing a silicon solar cell with the semiconductor module involves modeling the p-n junction physics in software like Capsule Multiphysics to optimize performance. Key steps include defining the geometry, creating a mesh, adding the silicon material with doped p-type and n-type regions, and applying the drift diffusion equations to simulate the cell's electrical and optical behavior. The design is refined by analyzing the effects of factors like doping, contact placement, and material properties to improve efficiency. The step 1 is define two geometry and mesh. Uh, for geometry, creates a one-dimensional or two-dimensional model of the solar cell, which typically includes the p-junction contacts and other key features. The next step is meshing. Generate a mesh of the geometry for specific areas, such as the contacts. You can use mesh control to create a finer mesh for more accurate results, while ignoring certain boundaries for physics settings. Step 2 is add the semiconductor material. But the step 1 is material properties. Add the silicon material to the model from the semiconductor module libraries, and the next one is doping. Define the p-type and n-type regions by adding the dopants. For example, in a crystalline silicon cell, you will have a p-type base and an n-type emitter. Step 3 is set up the physics semiconductor interface. Use the semiconductor module semiconductor interface, which solves the coupled drift diffusion and the Poisson's equations. And the next is analyzing type. Analysis type. Choose an analysis type such as steady state, which is often used to simulate the solar cell's performance under constant illumination. The next one is boundary conditions. Set up boundary conditions for the contact, specifying parameters like work function and charge carrier concentration. And the fourth step is simulate and analyze. For point 1 is simulate. Run the simulation to generate results. The simulation will show how the cell's performance is affected by different design parameters. And what about the analyzed results? Analyze the results to understand the current voltage characteristics and other performance metrics. For example, you can analyze the effect of different doping concentration or geometries. The next is refine design. Based on the analysis, refine the design. For instance, if the simulation shows high leakage current, you may need to add isolation groups to the design. And what about the key design considerations? The first one is p-n junction. The p-n junction is the core of the solar cell, and its design is critical for efficiently separating photogenerated electrons and holes. And the next one is back surface field, or BSF. A p-positive layer at the rear of the cell, or BSF, can enhance performance by reflecting minority carriers back to the junction. And what about the light absorption? The thickness of the silicon wafer and the reflectivity of the contacts affect how much light is absorbed and how efficiently it generates current. Designs often involve a trade-off between maximizing absorption and minimizing recombination losses. And the next part is contact placement. The placement and design of the front and rear contacts are crucial for collecting and generated current without causing excessive shading or resistance. And the next part is leakage currents. It is important to prevent leakage currents, which can significantly reduce efficiency. Isolating grooves at the cell's edges are used to minimize these currents. A p-n junction is the boundary formed by joining a p-type semiconductor with an excess of holes or positive charge carriers and an n-type semiconductor with an excess of electrons or negative charge carriers. This junction forms a depletion region due to the diffusion of charge carriers across the boundary, and it is the fundamental component of many electronic devices such as diodes, LEDs, and solar cells. And what about the key features? The first key features is p-type semiconductor. This material has been doped to create an excess of positive charge carriers holes. And the next is N-type semiconductor. This material has been doped to create an excess of negative charge carriers or electron. The next part is depletion region. When the two materials are joined, electron diffuses from the N side to the P side, and holes diffuse from the p-side to n-side. This leaves behind fixed positive ions on the n-side and negative ions on the p-side, creating a region depleted of free charge carriers known as the depletion region. And the next part is electric field. The fixed positive and negative ions in the depletion region create an internal electric field that opposes further diffusion, establishing an equilibrium. And what about the applications? The first application is in diodes. The simplest p-n junction is a diode which acts as a one-way switch for electric current, allowing it to flow easily in one direction forward bias and blocking it in the other or reverse bias. The next application is LEDs, light-emitting diodes. When current flows through the p-n junction in forward bias, energy is released in the form of light. Solar cells is the next application. A p-n junction can convert light in, light energy into electrical energy. Photons from sunlight create electron-hole pairs, and the junction's electrical field separates these charges to create a current. The next application is transistors. The p-n junction is also a key component of transistors, such as bipolar junction transistors. And the next is back surface field, or BSF, is a region of solar cell with higher doping on its rear surface that improves efficiency by reducing the recombination of charge carriers. This higher doped layer creates an electric field at the interface with the lower doped bulk material, which repels minatory carriers and prevents them from reaching the rear surface where they would be lost. And how it works? The BSF region is created by adding a more highly doped layer, such as a layer to the back of the solar cell, typically a type wafer, and the interface between the higher doped and the lower doped regions creates a barrier similar to a p-n junction. This barrier pushes minatory carriers such as electrons in a type wafer away from the back surface. And what about the purpose? By reflecting minority carriers away from the surface, the BSF reduces recombination, which is the loss of charge carriers to recombination with majority carriers. And what about the result? This process improves the solar cell's performance by increasing the number of carriers that can be collected, which leads to a higher efficiency and fill factors. And what about the alternative technologies? While BSF was a significant advancement, newer technologies like interdigitated back contact or IBC and all back contact ABC cells move both electrical contacts to the back of the cell to further improve efficiency and eliminate front surface shading. And the next is light absorption in the silicon solar cells happens when photons with enough energy excite electrons in the silicon crystal lattice, creating electron hole pairs. This process is most efficient for visible light, which silicon absorbs well, and for some near infrared light, but it doesn't absorb wavelength longer than 1100 nanometer because the photon energy is less than silicon's bond gap energy. The absorption depth varies by wavelength, with shorter blue light being absorbed more quickly than longer near infrared light. And how it works. The first step is photon energy. Light is composed of photons, and for a silicon solar cells to absorb a photon, its energy must be greater than or equal to silicon's bond gap energy, which is about 1.5 electron volt. The next step is electron excitation. When a photon with sufficient energy strikes a silicon atom, it can give its energy to an electron, knocking it loose and creating a free electron and hold the empty space left behind. And what about the electric fields, which is the last step of this process? This electron hole pair then moves to the solar cell due to the internal electrical field creating an electric current. And what about the key properties? The first property is absorption spectra. Silicon absorbs light across the visible spectra and into the near infrared with peak absorption around 780 nanometer. Absorption depth, the depth at which photons are absorbed depends on their wavelength. And the next one is blue light, for example 450 nanometer absorbed between about zero point 0.4 micrometer. And the next one is green light, for example 550 nanometer absorbed between about 1.5 micrometer. And the next one is near infrared light, for example 800 to 1000 nanometer absorbed between about 10 micrometer. And then the next step is wavelength limit. There is no absorption for wavelengths longer than 1100 nanometer as the photons don't have enough energy to overcome the silicon band gap. Contact placement in silicon solar cells involves placing both positive and negative contacts to collect generated current with the ideal placement minimizing shading and maximizing efficiency. Common placement include a traditional front contact design or a passivated emitter rear contact or PERC or heterojunction design, where all contacts are on the back to avoid shading losses. And what about the designing advanced designs like back contact cells place both the front and rear contacts on the rear to eliminate shading. And what about the front contact design placement? The positive contact is a grid on the front surface and the negative contact is a full surface layer on the back. And we want to talk about the pros and cons. The benefits simple to manufacture and at disadvantage the front grid blocks some sunlight and leading to shading losses. And what about the rear contact designs? The first step is placement. Both positive and negative contacts are placed on the rear surface of the solar cell. And the pros is eliminates shading losses on the front, allowing more sunlight to reach the silicon and be converted to electricity. And the disadvantage is that it requires more complex manufacturing processes to pattern the contacts on the rear side. And what about the multi-contact designs placement? Both positive and negative contacts are placed on the front surface but with a different design. And the disadvantage is more efficient than front contact cells. And the advantage is more efficient than front contact cells, and disadvantage is more complex to manufacture than front contact cells. And what about the back contact cells? The first step is placement. Both positive and negative contacts are on the block surface, and the pros or benefits maximizes the active area for light absorption on the front side, which increases efficiency. And the disadvantage is that more complex and expensive manufacturing. Leakage currents in silicon solar cells are undesirable reverse current that reduce power output by flowing opposite to the photocurrent. They are caused by minority carriers and are sensitive to temperature changes, making them a significant factor in solar cell performance and a result of damage to the p-n junction. Minimizing leakage current is critical for efficiency and require careful design and control of manufacturing processes. And what about the causes and characteristics? The first is minority carriers. Leakage current is primarily due to the flow of minority carriers across the p-n junction. And the next one is temperature dependency. It increases significantly with rising temperature as more minority carriers are generated. And the next one is reverse bias. In reverse bias diodes, a small leakage current is normal. In solar cells, this leakage flows in the opposite directions to desired photocurrent, reducing the cell's overall current and power output. The next is damage. It can result from the stress-induced damage to the junction or other parts of the device, which can lead to increased leakage even without a complete failure. The next one is design implications. The first is efficiency loss. Leakage current directly subtracts from the generated photocurrent, which decreases the cell's efficiency and power conversion capability. The next is manufacturing and quality control. Manufacturers must focus on high-quality fabrication to minimize defects that can lead to leakage current pathways. And operating conditions, the performance of the solar cells is affected by its operating temperature, as leakage current is a function of temperature. A solar cell structure in most of today's solar cells and absorption of photons, which results in the generation of the current carriers and the subsequent separation of the photo-generated charge carriers take place in semiconductor materials. Therefore, the semiconductor layers are the most important parts of solar cells. They form the heart of the solar cells. There are a number of different semiconductor materials that are suitable for the conversion of energy of photons into electrical energy, each having advantages and drawbacks. In this chapter, the most important semiconductor properties that determine the solar cell performance will be discussed. The crystalline silicon or CSI solar cell, which dominates the photovoltaic market at present, has a simple structure and provides a good example of a typical solar cell structure. And the simulation shows the essential features of crystalline silicon solar cells. And absorber materials is a typical um, moderator, moderator Doped p-type square wafer having thickness around 300 micrometer and an area of 10 multiplied by 10 centimeter square, or 12.5 multiplied by 12.5 centimeter square on both sides of the crystalline silicon wafer. A highly doped layer is formed, and positive and negative type on the type side, and p positive negative type on the back side respectively. These highly doped layers help to separate the photon-generated charge carriers from the bulk of the crystalline silicon wafer. The trend in the photovoltaic industry is to reduce the thickness of the wafers up to 250 micrometer and to increase the area of 20 multiplied by 20 centimeter. In addition to semiconductor layers, solar cells consist of a top and bottom metallic ring or another electrical contact that collects the separated charge carriers and connect the cell to the load. Usually a thin layer that serves as an anti-reflective coating covers the top side of the cell in order to decrease the reflection of light from the cell. In order to protect the cell against the effects of outer environment during its operation, a glass sheet or other type of transparent encapsulant is attached to both sides of cell. In case of thin film, solar cells layers that constitute the cell are deposited on a substrate carrier. When the processing temperature during the deposition of the layer is low, a wide range of low-cost substrates such as glass sheet, metal, or polymer foil can be used. The first successful solar cells was made from crystalline silicon, and crystalline silicon is still the most widely used photovoltaic material. Therefore, we shall use the crystal silicon as an example to explain semiconductor properties that are relevant to solar cell operation. This gives us a basic understanding of how solar cells based on other semiconductor materials work. The central semiconductor parameters that determine the design and performance of a solar cell are concentrations of doping atoms, which can be of two different types: donor atoms which donates free electrons, Nd, or acceptors atoms which accept electrons, Na. The concentration determines the width of the space charge region of a junction, and it is mobility or micro, and diffusion coefficient, which is d, of charge carriers that characteristics carriers transport due to drift and diffusion respectively. And the third one is lifetime or tau, and diffusion length is L, of the excess carrier that characterize the recombination generation processes. And the fourth section, band gap energy or EG absorption coefficient, which is alpha, and the refractive index, which is N, they characterize the ability of a semiconductor to absorb visible and other radiation. The next is atomic structure. The atomic structure of a silicon atom is 14. It means there are 14 electrons orbiting the nucleus. In ground state configuration, a silicon atom has four valence electrons. These valence electrons are most important because they form the bonds with other silicon atoms. The two silicon atoms are bonded together when they share each other's valence electron. This is a so-called covalent bond that is formed by two electrons. Since silicon atom has four valence electrons, it can be covalently bounded to four other silicon atoms. In the crystalline form, each silicon atom is covalently bonded to four neighboring silicon atoms. All bonds have the same length, and the angles between the bonds are equal. The number of bonds that an atom has between its immediate neighbors in the atomic structure is called the coordination number of coordination. Thus, in single crystalline silicon, the coordination number for all silicon atoms is 4. We can also say that silicon atoms are fourfold coordinated. A unit cell can be defined from which the crystalline lattice can be reproduced by duplicating the unit cell and stacking the duplicates next to each other. Such a regular atomic arrangement is described as a structure with long-range order. A diamond lattice unit cell represents the real lattice structure of single crystalline silicon. And here, this simulation shows the arrangement of the unit cells, and it shows the atomic structure of single crystalline silicon. One can determine from this simulation that there are effective 8 silicon atoms in the volume of the unit cell, when a lattice constant of crystal silicon is 5.4. One can easily calculate that there are approximately 5 multiplied by 1022 silicon atoms per centimeter cubic. This simulation shows the crystalline silicon atomic structure with no foreign atoms. In practice, a semiconductor sample always contains some impurity atoms. When the concentration of impurity atoms in a semiconductor is insignificant, we refer to such semiconductor as an intrinsic semiconductor. At practical operational conditions, for example room temperature, there are always some of the covalent bonds broken. The breaking of the bonds results in liberating the valence electrons from the bonds and making them mobile through the crystalline lattice. We refer these electrons as free electrons, henceforth simply referred as electrons. The position of a missing electron in a bond, which can be regarded as positively charged, is referred to as a pole. This situation can be easily visualized by using the bonding model shown here in this simulation. In the bonding model, the atomic cores, atoms without valence electrons, are represented by circles, um, and the valence or bonding electrons are represented by lines interconnecting the circles. In case of crystal silicon, one silicon atom has 4 valence electrons and 4 nearest neighbors. Each of the valence electron is equally shared with the nearest neighbor. There are therefore 8 lines terminating one each circle. In an ideal silicon crystal at 0 Kelvin, all valence electrons take part in forming covalent bonds between silicon atoms, and therefore there are no free electrons in the lattice. This situation is schematically shown here. In the at temperatures higher than 0 Kelvin, the bonds start to break due to absorbing thermal energy, and this process results in creation of mobile electrons and holes. Here, in the simulation shows a situation when a covalent bond is broken and one electron departs from the bond, leaving a hole behind. And here in this simulation, you can see that we selected silicon with the properties such as Aurora mobility model, power law mobility model, Auger recombination, direct recombination, Shockley-Read-Hall recombination, Fletcher mobility model, Coffey-Thomas mobility model, semiconductor materials, Lombardi surface mobile model, and impact ionization, Slot-Bohm model, and Giant Rolleston model, and class and unified mobility. And here you can see the property, for example, relative permittivity, electron lifetime, whole lifetime, band gap, electron affinity, effective density of a state, effective density of a state based on volume or valence band or conduction band, electron mobility, whole mobility, thermal conductivity, density, heat capacity at constant pressure, electron mobility reference, whole mobility reference, electron mobility reference minimum, whole mobility reference minimum, and electron reference impurity concentration. Whole reference impurity concentration, alpha coefficient, mobility reference minimum exponents, mobility reference exponent, impurity concentration reference exponential, alpha coefficient exponent, reference temperature, electron mobility reference, whole mobility reference, electron exponent, whole exponent, reference temperature, other recombination factor electrons, and Fletcher mobility, and etc. that I have described here. For each one there, for example, for class and unified mobility, this property will be repeated. And the physical module that we have used, you can see that we have a one-dimensional solar cell with silicon as material, and you can see the semiconductor material, zero charge, insulation, continuity or heterojunction, initial value, metal contact 1 and 2. Uh, you can see metal contact 1 and metal contact 2. And finally the result, its energy level, the first plot. The next is carrier concentration, electrode potential, doping, generation recombination, and finally current voltage curve and power voltage curve. Thank you so much for watching my tutorial video until the end, and also you can download this simulation from github.com/mathscience.